In the second part of this question, we need to find out all the different forms of these wave functions that we solved in the first part. So we'll start with the ground state wave function, spatial portion of the wave function. We found it to be looking something like this, where this parentheses ... is some global constants, and this one is actually a different global constants, but it doesn't really matter for this part of the problem. We just need to draw this wave function in terms of space and in terms of the value of the wave function. So the first thing that we can notice is that the only parts that actually depend on x is just this negative exponential. And from what we know from negative exponential, that's going to end up being a Gaussian curve, which I'm going to draw absolutely terribly. Here we go. So we'll just say that's a nice Gaussian curve. And of course, where x equals 0 right here, this whole term goes to 1. And then all that's left is these global constants, which is not really relevant for this question, but if you want to know what it is, you can go back to the first part of the video. But for the most part, that's what the form of the wave function is going to look like for the ground state of the simple harmonic oscillator for this problem. And we're going to use this as a canvas to do the rest of the different forms of the wave functions, the excited states. For example, the first excited state, it's going to look a little bit different. This one actually has an x out in front here. So what we do is we know that the wave function, of course, looks like this for the ground state, but then it's almost kind of like modulated by this x, which is just a line here. So that means everything that was on the left-hand side of the wave function portion is just going to kind of be switched around, and then it's going to end up looking something like this again. So we'll go ahead and draw that out. So again, we're just kind of modulating that original ground state wave function where it just kind of trails asymptotically on the x line, goes across to 0 here, and then goes back asymptotically here, which is not, I don't think that's actually a valid function, but you know what I'm trying to say here. That's what it's mainly going to look like here. All right, so that's the first excited state. Now the second excited state gets a little bit more complicated. So now it has an x squared minus 1 out in front, but everything else is generally the same. So again, it's just going to be the same wave function, but it's going to be modulated by x squared minus 1. So if we just look at the x squared part, x squared, of course, is a parabola that looks something like this. So the ground state wave function is going to be modulated by this parabola. In addition, so let's go ahead and let's just go ahead and draw that right now. So when it's modulated by a parabola, it's going to look something like this. All right, don't mind the squiggles here. And then with it modulated like that, it's gonna just gonna stay there, but with this minus 1x here, so at x equals 0, this whole term is gonna go to 0, this term will go to 0, and all that's gonna be left is a negative 1 times this glob of constants. So it's just gonna be shifted down to some value, or well, not the whole thing, but this point right here is just gonna be shifted down to that negative glob of constants right here. So we'll just say this is the negative ... that's out in front. So if we redraw our wave function to make it follow that modulation, it's going to end up looking like that. So that's the different forms of the excited first, second, and ground state of the simple harmonic oscillator for this problem.